Hey folks. Okay, well, I want to go through exceptions and assertions and give you a feel for a different form of catching problems, I'll call them errors for the moment, in our code and where it can be used and some of the drawbacks and some of the advantages of it. So far, everything we've done with error checking has just been purely manual. If we want to check for a bad value somewhere along the line, we stick in an if statement that says if blah, 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 do something about it. Well, there are a couple of sort of different layers of things that can go wrong. We've got the normal idea where, we ask the user for some data and we want them to enter a number between 1 and 10 or something like that. And sometimes they enter something that's not a number, or sometimes they enter something that's too big or too small. And so we've got the usual sort of just checking user data to make sure that the information is actually correct. Or same idea with reading information from a file, right? We read information from a file and just check that it's following the format we expected, check that the file actually exists and all that sort of thing. So there's lots of fairly normal error detection that we can carry out. But there are some other things that can go wrong during the execution of a program. We can hit scenarios where a data structure has been corrupted. We're working in a binary search tree that we think has been built correctly. All right, our code built it. We think our code is correct. It should be okay. And we discover during the course of execution that something's wrong. Or we perform some kind of a computation and the computation actually turns out to be too large to hold in an int or a long or a double or whatever it is we're using to store the values. And we get some kind of overflow or underflow error, or we get things like infinite recursion. We get all sorts of possibilities, all sorts of things that can go wrong. Things like we try and allocate a new array, or we try and allocate a new object and it fails because there isn't enough memory in kind of one lump to satisfy the request, or it fails because we've given a negative size. Our usual problems of trying to access things through null pointers or dangling pointers, all sorts of things that can go wrong of different degrees of severity and different degrees of how normal, if you like, it is. It's really normal for a user to enter an incorrect piece of data, right? Just a typo or just misunderstanding how to use the program. But it's less normal, if you like, to have things like an overflow error in your computation or to have a failed memory allocation. So some things we regard as just part of normal processing, and some things we regard as kind of beyond the pale of just normal processing, normal error handling. And so we're typically going to refer to these as exceptions, right? Things that, exceptional circumstances, if you like, things that are beyond the pale of the norm, things that are outside what we would handle in just the normal control flow of our program. And so we're going to have a different means of dealing with those. And I'm actually going to introduce a third category, this idea of assertions, where we can make a statement about something that we believe must absolutely categorically be true at a certain point in our program. If I've gone through and allocated memory and stored a pointer to it and I've checked that the allocation succeeded, then a little ways further down the program, if I haven't changed the pointer, that pointer shouldn't be null. And so I might make an assertion that, at this point in the code, this pointer absolutely should not be null. If it is, something in my code is broken. And so we can make these assertions about important things that we think must be true at a certain point in the code. And if they're not, then it indicates a development problem. It indicates an actual programming error. So we're going to look at these kind of different categories of problem and how we can deal with them. All right. So again, this sort of different layers of handling things. Some error checking that's best handled at just the regular old manual level. If user input is less than 0, blah. There are some things that are unusual, but not entirely unexpected. Again, if we do new blah, 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 some size, then we know that there are going to be times when it's going to be out of memory or times when it's just going to fail to allocate. So it's not entirely unexpected, and it doesn't mean our code is wrong, but it's something that we still have to handle. So that will kind of fall into our exceptions category. And then again, things that we deem should never be possible, because if this thing does happen, it means that our code is actually incorrect. So we'll have these different layers: regular error handling, exception handling, and then assertions. So for this new middle layer, the exceptions, what we're going to do is specify a block of code in which we want to check for exceptions. And so again, we're going to have kind of these open and close brackets around this block of code saying, okay, I want to check for exceptions in this block of code. And the keyword at the start of that to indicate that we're going to be doing exception handling is try. So it's essentially saying attempt this block of code, and we're going to try and detect if something fails. And then if something does fail, we're going to try and catch whatever it was and deal with it later on. So the way it works is you have these try blocks, try, and then a bunch of code. And then following that, you'll have a catch block where we're going to deal with anything that came up with, any exceptions that came up in this try block, any exceptions that we actually detected. So what happens is there are certain kinds of exceptions that are just automatically thrown. I'll talk about those in a minute. But if we detect something where we explicitly want to generate an exception and say, this is a problem, then we can use what's called a throw. So you stick in an error test and say, if for instance this pointer is null, that shouldn't have happened. I want to generate an exception saying, I can't do my normal processing anymore because something's broken here. Something's incorrect here. So we can issue this throw command along with some kind of data that we want to pass as information to be used when we process that exception. So in this case, I'm just going to toss this string saying, okay, let's throw this string out as the data for the exception that I just detected, this p being null. So the catch block has to be set up to catch the same kind of data as you threw. So in this case, I'm throwing a string, so I've got to catch a string. So my catch says, okay, well, if somebody throws an exception that's a string, I'm going to catch it. It'll wind up in my eMessage parameter. And then inside all I'm doing here is just saying, okay, I caught this exception and it's whatever this was. So what happens, is as this code executes, if everything goes normally, right, it plugs along. If p isn't null, then, it doesn't throw an exception. It just goes on with the rest of the code. And this catch never gets activated, and it just goes on with whatever's in the program after the catch. So this try catch is kind of lumped together, and it either does the try and then moves on with the rest of the program, or it gets partway through the try, throws an exception, does the catch, and then goes on with the rest of the program. So this is the idea. And as long as what you're throwing matches what you're catching, the catch can handle it. So I just want to quickly run through a couple of little chunks of code to demo that, and then we'll see where we get to here. So what have we got? Let's do this simple exception here. So this is a little block of code doing kind of like what we just showed. What have I got? Oh no, this one's doing get the user to enter two integers, and we'll divide the first one by the second one. So give me a numerator and a denominator, and I'll divide the numerator by the denominator. And what we're going to regard as an exception here, again, this is a pretty trivial example, but what we'll regard as an exception is if the denominator is 0, because we can't do a divide by 0, it'll crash. So I'm going to have this try block. Well, I'll have my usual variables to hold my numerator and denominator, ask the user to enter two integers, read them in. And in my try block, I'm going to read the two values in. And if everything goes well, I'm going to print out, the numerator divided by the denominator is, whatever, num divided by denominator. But in between, I'm going to have this little block of code to catch the possibility that that denominator was actually 0. So if the denominator is 0, then I'm going to create the string, divide by 0, so this is basically just an error message. And I'm going to throw it. I'm going to throw this string saying, I detected an exception. So if that happens, it'll skip the rest of this try block and it'll go straight on and look for a catch that can take a string. And it finds one right away, this one, and pretty much just spits out exception, whatever the error message is, and then goes on with the rest of the program. So if they enter something that's valid, 3 and 1 or something like that, then it's going to read in their values, print out what 3 divided by 1 is, and then go on and hit the rest of the program and print by, and this catch block never gets run. If they enter a 0 for the denominator, it's going to go through, throw this exception, print out this error message, and then go on with the rest of the program. So let's just make sure that that actually works and hope that I actually debug this. So we'll give that a try. And that, here, let's actually call it something. So let's run our simpx, and it should ask me for 2 integers. I'll do it normally the first time, so give a 3 and a 1, and 3 divided by 1 is 3. Great, and it goes on with the rest of the program. And if I run it and give a 0 for the denominator, then it detects that denominator as 0, throws the exception, the catch handles it, and then it goes on with the rest of the program. So far so good. All right. Now, again, I know catch looks like a function, but it's not. It's basically just saying, okay, I'm gonna capture what you threw to me, deal with it, and then move on. So this isn't like a catch and return. It doesn't go back to the try block. What we could do, so often we've got these scenarios where if something doesn't work, we want to try it again and try it again and try it again. If we wanted to do that in this scenario, then we would have to do our try and our catch. And if it worked out, fine, we can move on with the rest of the program. But if it didn't, suppose we want to go back and try that and attempt that try catch again, we would have to enclose the whole thing in a loop. So say, okay, well, let's keep doing this until we're done, until we got a success. Do our try. If it succeeds, set done to true. Otherwise, if an exception gets handled or an exception gets thrown and caught, we'll deal with that here and go back and try again and again and again and again and again. So we can do that. I'm going to, again, just run through a quick example to make sure this makes sense. And this is our loop example. So again, similar sort of idea. We're going to do that same numerator and denominator example. I've got this while loop around the outside that says, while we're not done, keep attempting this. So I'm going to start off with done is false. And I'm going to go through that inside. I'm going to go through the cycle. Ask them to enter 2 integers, read them in, have my little block of code enclosed in a try where if the denominator is 0, we'll throw an exception. Otherwise, we'll just go straight ahead and print out the results and set done to true so that we get out of the loop. And again, the exception handling is basically just saying, I can't process this, your denominator is 0. And then eventually we get out of the loop and we print our by. So if we give this a try, and we'll try our loopx. So again, if we give, say, a 0 for our denominator on the first try, that first round through, that first pass through the loop, the try block throws an exception, it gets caught, and we make another pass through the loop, right? And so again, we can keep going. If I keep entering 0s for our denominator, it's going to keep going through that loop, and eventually, we give something that's valid, and it proceeds normally, and we dump out of the loop. So again, just keep in mind that if you want your try catch to keep cycling through, you've got to enclose the whole thing in a loop. All right. Now, in terms of those parameters, I said that our throw can throw something, our catch can catch it if the parameter types match. So that kind of implies that we can have different types of parameters for our catches, but it also means that, if we have just a single catch block there, it might not catch the thing we threw if they're different types. So we can actually have a sequence of different catches after a try block. And what'll happen is if an exception is thrown, it'll look at the first catch and see if the parameters match. And if they don't, it'll go on to the second one and see if the parameters match. And if it doesn't, then we'll go on and look at the third one. It'll keep looking at these different catch blocks until it finds one that actually matches. And actually, if it can't find one that matches, then we're going to terminate the program and say, you threw an exception that I couldn't handle. Now, this does mean that since it's going to perform the first catch block that matches, we want the catches to go from kind of the most specific to the most general. So remember when we were talking about dynamic binding of classes and assigning ancestor classes to descending classes to ancestor classes and that kind of thing? We had this idea that you could have let's say a parent object and a child object and a grandchild object, and you could assign a grandchild to a parent, for instance. Well, if my catching was catching the really general one first, the parent, and then my next catch was trying to catch a child, nothing would ever reach that catch a child because it would always get caught by the parent. So you start with the most specific ones in your catches and go on to the most general in cases where they do overlap. In lots of cases, the parameter lists are completely distinct anyways, and it's not a problem. However, again, I just wanted to go through a quick example to demo that. And this was our multi-catch. So in this case, again, we're just going to keep plowing ahead with that same example where we've got a numerator and a denominator. But just for the sake of argument, I'm going to have two different types of exceptions we can throw. We'll still have if it's a 0, we'll throw in a string for a divide by 0. And if what they passed as the denominator was negative, then again, just for the sake of argument, we're going to throw a different kind of exception. So we'll actually tell them what kind of a denominator it was. And so we're going to throw a string for the first kind of exception and an int for the second kind of exceptions. And so when we catch them, if we catch the string, we'll just print it out. And if we catch an int, we'll assume it was because we had this negative case, and we'll tell them, negative denominator, and we'll print out whatever it was. So if they throw a string, we catch it here. If we throw an int, we catch it here. And so hopefully this one works out as well. And so again, if we do something like 5 and 2, again, it's doing integer division there, so 5 divided by 2 is 2. That works out fine. If we try a 5 and a 0, we get the divide by 0 exception. And if we do a 5 and, say, -1, we get the negative denominator exception. So it can actually detect which kind of exception is being thrown based on the data types thrown. Alrighty. One of the things that you might have spotted in those lists is that best practice is to do our catch by reference, not as a const. So just as a heads up, the compiler will warn you if you're throwing, or if you're trying to catch as a const, or if you're trying to catch by value. All right. I kind of diverted for just a second there into talking about the idea of throwing objects and catching objects, having classes as the kinds of data that we were throwing and catching. And this is pretty normal because often there's a lot of information that we want to pass as part of an exception, or you want to say, this went wrong, this was the kind of thing that happened, here was the data that we were working on, blah, 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 blah. And if we're going to throw a whole bunch of things and we want to be able to do some analysis on it, it would help if we could actually have a bunch of data fields and some associated methods to deal with that kind of exception. So we often create a class to represent the type of exception and throw that class? Well, there's actually, in the exception library, there is a class in the standard namespace, so std exception, that is used for exactly that purpose. It's used as a base class for kind of predetermined types of exceptions, and we can derive our own classes from that. And so we can build up this entire hierarchy of different types of exceptions we want to be able to handle with this one general exception type at the top of the chain, if you like. If I don't know what kind of exception it was, I just know something's wrong, I can throw one of these things, and I can catch one of these as a last ditch, I know something went wrong, but I don't know what it was, sort of catch-all. So this exception library exists as the basis for a sort of a hierarchy of things that we want to treat as exceptions. So this hierarchy has a bunch of built-in ones. There's one called bad alloc that is actually thrown by new if new fails to allocate memory. So we can use that instead of the kind of null testing that we've been talking about so far. Things like bad casts for when typecasting goes wrong, when you try and cast one thing to another, but there's no known conversion between the two. Bad type IDs where you specify a bad type. Bad exceptions, logic failures, runtime errors. So there's a handful of exception types built into this library, and a lot of them are thrown automatically in certain circumstances. A couple of them have sort of a hierarchy of their own. I think that should actually be logic failure there. However, they've got a variety of different subclasses, so that includes domain error, invalid argument, length error, out of range. The runtime errors include overflow errors, underflow errors, range errors. So again, there's this built-in hierarchy. And when you're creating your own types of exceptions, there might be times when you build it derived straight from exception, but there might be times when you decide that it fits kind of in one of these other categories and you derive from one of these other beasts. So I wanted to do a quick example using new, since it's something that we've done a lot of error checking for previously, trying to check if something's null. So the idea is when we call new, so I'm trying to create an array of integers or something like that. So my pointer is a new array of integers of some size. Well, we know that new can fail. What typically happens if new fails is that it throws an exception of type bad alloc to indicate that it did in fact fail. So I can have, if I've got a block of code where I'm doing an allocation and then doing a bunch of stuff with it, then what I can do is enclose it in a try block and say, okay, well, I want to do exception handling in here. New automatically throws this exception if something goes wrong. And so I can throw a catch afterwards where I'm saying, okay, well, I'm going to look for a bad alloc just in case that came out of new. And so we can essentially attempt our allocation and see if it worked or not. So once again, I want to just briefly dive into an example here, and we'll contrive a couple of cases where new actually fails. So I've got this in except new. So what I've done here is to create a class that's got a really big array in it. And we're going to try a couple of different things. So we'll try, we can try allocating an instance with a negative size, for instance, and it will throw. Or I can try allocating an array of these things. So if my class has a huge array in it and I create an array of these classes that's really big, then again, it can go through and crash. So variety of different ways it can work. I'm just going to show it with the negative size one for just a moment. So we're going to try and allocate an array of a negative size. It should throw a bad alloc error, and so we should wind up catching it down in our default catch here. So we can give this a whirl. Let's try our accept new, and you know, I should probably give it a name. Let's call it enu. And we'll try running enu, and again we had negative size in there, so the new should fail. And yeah, new failed in try. It got caught in our catch. Null pointer got returned from new. We know what's going on. Maybe just as a quick example about the sort of general to, or specific to general idea, let's do a quick tweak to that. And we'll throw in 2 catch blocks here. So let's say that we tried, and again, this is to demonstrate that this is a bad idea. We'll check for a general exception first. So if just any old exception happens, we'll catch it here. And if a bad allocation exception occurs, we'll catch it here. And again, what's going to happen is that because we're checking for the general one first, it's going to find that and say, oh, this matches a general exception. And it's going to do this, and it's not even going to go on and check the second one, I think. So let's give that a try. Ah, yeah, there we go. Okay, so the compiler is actually warning us that that's what we're doing, that we've got this general exception type first, and it's going to mask the second one. So the bad alloc can never happen because it's always going to get caught by this standard exception one. Oh, thank you, compiler. So if we did it the other way around, if we put our specific one first and our general one second, then it works out okay, and we're still going to catch it in the first one, which is what we wanted. If there was an exception that got thrown that wasn't a bad allocation, then it would go on and get handled by that second case. Alrighty. There are certain circumstances where we can turn off exception handling to a degree, or throwing of exceptions to a degree. New is one of the examples. You can throw in an std NoThrow specifying that I want new to not throw an exception if it fails, and instead to return null the way we've been using it. There are some limitations to that. It only works if the thing that we're trying to allocate is a class, and it only works if the failure is because there was insufficient memory contiguously available to throw it, or to satisfy the request. If we get new failing because, let's see, what's an example, because the size is negative, then it'll still actually throw a bad alloc exception instead of doing this. So we can sometimes, to a limited degree, disable our exceptions. Again, we can create new exception classes of our own, so I could derive my own special kind of exception. And again, we're typically going to try and base those on the existing standard exception library. So I might derive this from exception, or I might derive it from bad alloc if there's some specific new kind of allocation failure exception that I want to describe. One of the things that we should be aware of is that we can have exceptions that are thrown inside a function and that are caught outside the function. So you can wind up with these sort of layers of exception handling where your function has a try block in it and a couple of catches, and your function throws in that try block throws an exception. The different catches there don't manage to handle it, and it goes sort of outside the function, if you like. And if whoever called that function made that call from inside a try block, we can try and catch on the outside. And so what I'm going to take a look at here is an example where we've got a main routine with a try block in it, and inside that we call a function. And in that function, it's got a try block, and inside that it calls a function. And we've got this other function that's got a try block in it, and inside that it does a bunch of stuff, possibly throws an exception, might be able to catch its own exception, might not. If it doesn't, then the function that called it might be able to catch it, might not. If it doesn't, the main routine might be able to catch it, might not. So we'll play with just a quick example here to get this kind of hierarchy of exception handling going on. What did I call this one? That looks like our exception hierarchy. How about that? We'll take a look. All right. So what I'm going to have is a few different types of exceptions to demonstrate this. So we're going to have that STD exception as the most general one. And I'm going to have, oh no, sorry, in this case, I'm not going off of the STD exceptions. I've got my base exception class 0. I've got one derived from that. That's my exception type 1. And then another one derived from that that's an exception type 2. So we've got these 3 different layers of exception classes. 0 is the base, 1 is derived from that, 2 is derived from that, and they've each got a print method in them that can print out information coming from the exception. And then we'll follow that kind of setup that I was talking about before, where in my main routine, I'll have a try block where it calls a function. Calls F2. And in F2, we'll have a try block where we call F1. And in F1, I'll have a try block where we try and do a bunch of stuff. So in this case, I'm going to say if you pass me a value that's 0, I'm going to throw one kind of an exception. If you pass me a 1, I'm going to throw a different kind of exception. If you throw me anything else, I'm going to throw a different, or you pass me anything else, I'm going to throw a different kind of exception. So it's going to potentially, based on whether it's given a 0, 1, or something else, throw one of 3 different kinds of exceptions. If it throws a type 2, we'll catch it right away. So that was the most specific one, if you remember. You throw a type 2, we'll catch it right away. But if not, then the attempt to catch has to look outside this call to F1. And so we're back in our F2. And so it looks in F2's catches. And in F2, we can catch a type 1 exception. So we can catch the kind of middle layer of exception. But again, that might not catch it. If somebody throws the most general one, if it throws a 0, then this won't catch it either. So it falls back to the outer one where we had this try catch block that could catch that general one. So we can have these sort of nested layers of tries and catches, and it'll keep looking for, can somebody handle my exception? Can somebody catch the thing that I've thrown? And so what we've got in the main routine here are just 3 different examples of calls to F2. We'll call F2 and pass it a 0, which gets passed along to F1, which makes it throw the one kind of exception. And we'll do a similar idea passing it a 1, which throws the other kind of exception. And we'll call it again with an F2, and it'll throw yet another kind of exception. And we'll see them caught in 3 different places. We'll see one of them caught in main, one of them caught in F2, and one of them caught in F1. So let's give that a quick try. Okay, so we see one caught in main, one caught in F2, and one caught in F1. Yay! So we actually got the right idea going on here. So we can actually catch in the function, the most narrow function, if you like, with the most narrow catches. And if not, it goes on and, see if the function outside that catches more general stuff, and have the most general of all in our main routine. So if we're deriving from the STD exception class, so what we would quite often do is say, well, I'm going to derive this from that STD exception. And then in my main routine, let's actually do that here. So I could say I want this to be based on that public STD exception class. So I should include exception. And in my main routine, I'll throw in one more outer layer here. What if something gets thrown that isn't one of these special ones I've derived? What if something got thrown that was just some other kind of general exception? What if somehow an overflow or something got thrown? So I can throw this most general form of exception handling in and say, okay, if you catch anything else, I'll deal with it here. So maybe I stick in a message like general exception or something like that. And the general one doesn't have a print, so I shouldn't be calling that. But again, we can go through and say, all right, let's have this outermost layer of just in case, right? Something to catch anything else that I haven't thought of, haven't addressed. And this actually isn't going to behave any differently because I'm not throwing any other kind of special exceptions. But we can add in that sort of layer upon layer upon layer idea. Oh my goodness, and I didn't show you any of that. All right. Let me quickly run through that idea again. How about I actually show you the code this time while I'm going through it? So again, the idea was we've got this, I've got these layers of exception classes. My exception 0, my most general, and it's got a constructor and a print method. And my exception 1 derived from that. That's kind of my middle layer, if you like. And again, it's got a constructor and it's got a print method in it. And I've got my most specific one derived from that. So we've got exception 0, derived from that I've got exception 1, derived from that I've got exception 2. And this can, again, have a print and a constructor. And my functions, F1 is the one that can throw exceptions. And it's got a try block and says, okay, well, you pass me a value. And if it's a 0, I'll throw one kind of exception. If it's a 1, I'll throw a different kind. If it's anything else, I'll throw something else entirely. And I'll catch the most specific ones. So if you throw this exception 2 type, I'll catch it here. Anything else, I'm not going to deal with. So anything else drops out to whoever called me. Right? So F2 called F1, and F2 had that in a try block, so it can catch errors that come out of F1. So if 1 throws an exception and doesn't handle it, it comes back here, and we try and catch it. And if it's a type 1, we can actually catch it. If it's not a type 1, we can't catch it here either. So, well, main was the one that called F2, and it had that in a try block. So if F2 throws an error or an exception that it can't handle, then I can handle it. So I'll try catching it, and if it's a general one, or if it's an exception 0, 1, I'll handle it here. And if it's not, then I will see if it's just a general whatever kind of exception and deal with it. And again, the demo was showing that the 3 different types of exceptions do actually get caught in the 3 different places. Right? Main called F2, called F1, F1 called threw the exception, and in one case we managed to catch it right there in F1 where it was throwing the most specific kind. In one case it got to the outer layer and we caught it in F2, and in one case it made all the way back to main where we caught it. So we can create these hierarchies of exception handlers, and we can catch exceptions that were thrown by functions that we called if they didn't deal with it themselves. All right, let's actually show you the same thing I'm looking at on my screen. Alrighty, and so we've got this idea of throws and catches across different functions. And again, this is pretty much running through the exact idea that we just looked at. We've got this exception hierarchy where I say I'm going to have my exception that's derived from the general one. I'm going to have a more specialized derived from mine. Maybe I've got even a more specialized one derived from that. And then we'll have these sort of nested layers of classes or functions rather, where main calls F2, calls F1, F1 throws the exception, and it might get caught right here, or it might escape and make it back to F2 where we catch it, or that it might even escape that and get back to F1 where we, or main where we catch it. Blah. Now, there are advantages and disadvantages to this. One of the advantages of having these try catch blocks is that it lets us take the ugly code that might be dealing with the exception and move it to someplace else. Right? In this case, sometimes even moving it out to the calling function or the main routine and deal with it out there. And so it separates our, if you like, normal logic flow from dealing with these weird edge cases that we might have to handle once in a while. So that can make our regular logic flow cleaner and easier to read. It can make it more difficult to follow the trail to where the exception actually gets dealt with. So it can make some things cleaner to read, some things more difficult to read. It can allow us to sort of centralize the exception handling. So if it was possible that either F0 or either F1 or F2 or main could have thrown this one particular type of exception that was going to get caught and handled in main, then I've just got the handling for it in main. I'm not having to put that in both places. One of the other drawbacks is that it does increase the compile. It throws more work on the compiler to go through and build all this. So it does increase the compile time. It does increase the size of the executable. For the most part, having the exception handling in as sort of a safety valve doesn't have a huge hit in terms of runtime behavior unless the exception actually gets thrown. So there is a performance penalty, not a huge one, unless the exception actually gets thrown, in which case it can be a fairly expensive process for it to find and invoke the right exception handler. There are going to be times when either your memory is so tight or your timing constraints are so tight that even the kind of marginal cost of the just checking to see if an exception exists is going to be too much. But for the most part, in normal development and in sort of a normal programming environment, you're typically going to regard the benefits as outweighing the costs. But again, that's kind of it's a cost-benefit analysis. Most of the time, if you're developing a new project and it's not time critical, memory critical, you're going to regard it as worth it to go with the idea of including exception handling. If you're trying to retrofit old code, sometimes that it can be more costly than it's worth to carry out that retrofit. But in general, for new code, new projects, you're typically going to regard it as a win situation. All right, the last one I wanted to mention was the idea of assert and assertions. So this was the idea where I've got something that I'm positive must be true. If it's not true, it's because my code actually contains an error someplace. So you do something like you've got some data structure and you're working your way through it. And at some point in your code, you're certain that the pointer couldn't possibly be null here. I know from the way I structured my code that for me to get here, the pointer must actually be pointing at something real. I've done all my appropriate error checking somewhere else. If it gets here, it's got to be non-null. If it is null, it indicates that there was an error in your code somewhere back there because you got here and it isn't what you thought it had to be. So one of the things that's often done during development is to stick in these tests that are essentially an assertion of something that I think must be true. If this thing isn't true, my code is broken somewhere, or somebody's code is broken somewhere. And what happens with these assertions is as the program is running, if it hits the assertion, it does the test to make sure that the condition is actually true. If the condition fails, then it says, stop the program now, tell him what line we're on, tell him what condition was violated, and the developer can see that, oh, something must be broken. So the idea is that you only use these during development to figure out where there might be problems in your code. Hopefully you've eliminated all of these before you ever get to releasing the sort of final production code. So the syntax is that we include the CAssert library, and we use the statement assert and whatever condition you think must be true. So if I'm certain the pointer can't be null, then I'm going to assert, the pointer is not null. And say this was on line 200, and if we compile and run and it hits this point and the pointer is null, then it's going to terminate the program and say something like assertion failed, line 100 or whatever it was, the pointer not equal null. So it tells you what condition was violated, what line of the program it was on. So you can get extra information to help you with the debugging and development process, if you like. So maybe we'll just give a quick try of that. Did I actually create an assertion? I think I did. Yeah. So here's an example where, and again, just a toy example, but I've got a couple of integers. I've got a pointer. I'm going to make it point at one of these things. And as far as I'm concerned, I'm going to make it point at the larger of the two, or smaller of the two, I guess. Yeah. So it's going to point at whichever int has the smaller value. So I'm going to start off with it pointing at A, and if the value of A is bigger than B, I'll make it point at B instead. But we do a bunch of stuff, and I'm certain that, if my bunch of code, whatever it is in here, doesn't change that pointer, then I'm pretty certain when I get down here, that pointer can't be null. And it's pointing at one of two real things. It can't be null. So I stick in this assertion that pointer isn't null. And as long as that's true, as long as the pointer isn't null, it goes on with the rest of the program and everything runs normally. And so, again, if we compile this and run it, then everything should be happy, and it says target value is 1, everything's fine. And now let's just show an example of what would happen if somewhere in our code we'd accidentally broken something. And so here I'm just going to deliberately set pointer to null as if that had accidentally happened somewhere in our code. Oopsie. Let's try that again. Okay. And so we'll try running this beast now that the assertion is actually incorrect, and we get this aborted. It tells me I was on line 14 in assert.cpp, and it tells me the condition that failed, right? It tells me what part of the condition failed. So we can actually go through and include these as an extra helpful debugging tool. Again, the idea is that we would never want to see an error message like that crop up during real execution for a user, but while we're developing, they can be a very handy tool. All right, I think I will leave our exceptions and assertions material there, and we'll see how we go next time. Thanks, folks.